The objective of this video is to introduce the switching power pole primitive as a means to lead us into switch mode power electronics. So remember I said that there are two ways of thinking about energy conversion or voltage level conversion. The first way we introduced as being linear regulators, and the second concept I said was going to be fundamentally different, and that is switch mode power electronics. So we're going to start by going back to our linear regulators as a launching point. So we've talked about this in a couple of videos. I've sketched a linear regulator on the left side, and typically we model it as this equivalent model here in the center. So if we zoom in and take a look at the switch, we've been specifically talking about a BJT, which we then model as this variable resistor. So what does it mean to model a BJT as an equivalent resistor? So going back to your circuits class, ECE 340 and ECE 342, you learned that you can represent the current voltage characteristics of a BJT like this. Where when the device is operated in this region, we say that it is in saturation. When it's operated in this region, we say it's in its linear region, this linear operation. And when it's down over here, it is in cutoff. So this is a characteristic based on changing your base current into your BJT. So when you operate in this linear region, when you have a certain base current, your BJT looks like a resistor. So you could say that this is resistor based on base current 1. Here's the resistor based on base current 2, and the resistor based on base current 3, and so on. So that is to say that when we select our base current, when our op-amp, our feedback amplifier, selects our base current, we've selected the resistor value for our voltage divider network. And because of this fundamental voltage divider structure, we've commented that we have a very low efficiency for large differences in voltage between the input and the output. And furthermore, by observing this circuit structure, we can say that we have unidirectional power flow. And similarly, our voltage transformation goes one way. We can only reduce the voltage. So to be clear about this, on the left side of our equivalent model is our high voltage side, or unregulated side, and power can only flow from the high voltage side to the low voltage side, which is a logical conclusion of a voltage divider equivalent circuit. Okay, so while we said that linear regulators always operate in the linear region, when we introduce switch mode electronics, we will note that they always operate in either the saturation or the cutoff regions. That's to say, switch mode electronics always operate here, where the device is completely off, or they always operate over here, where the device is completely on. And also, we don't typically use BJTs in switch mode electronics. We often use MOSFETs. So you'll note that where our power consumption occurs in the linear regulator is when the device is active in this linear region. It looks like a resistor. You have a lot of loss. By using switch mode electronics and operating either the device completely on or completely off, we've removed the loss component. So what does this mean? Well, we've been talking kind of abstractly. Let's get down to a model of a switching regulator. And the fundamental equivalent model that we're going to be considering is going to be something called a switching power pole. I'm going to first draw this as a mechanical single pole double throw switch. So you can think about a light switch. Right? You've got one pole and two throws. So I'll abbreviate this as SPDT, and Single and double have meaning, so we can say that this is a one-pole, two-throw switch. So now I want you to do an active learning exercise. When I finish these instructions, I want you to pause the video, and I want you to sketch what a single-pole, triple-throw switch looks like. So pause the video now and sketch a single-pole, triple-throw switch, and when you hit the play button, you'll see me sketch it. So here is a single pole triple throw switch, and if you count the number of throws, you can indeed see that we have 1, 2, 3 throws and 1 pole. And our switching mechanism here can connect that pole to any one of the 3 throws. However, we're going to start by talking about the simpler case of a single pole double throw switch, where the switching mechanism can connect our pole to either of the 2 throws. Okay, so now let's talk about waveforms of this. Suppose you have a single pole double throw switch connected to a circuit as follows. So you can see that I've labeled the 2 throw currents as IT1 and IT2, and I've labeled the pole voltage as VP. The circuit that we've connected here consists of a stiff voltage source labeled as VT, just a DC source, and a DC output current labeled as IP, so a DC current of IP. And based on the switch position, whether the pole is connected to throw 1 or throw 2, you can see that the voltage at our pole is going to vary. So this is an equivalent circuit model. So similarly to how we modeled a linear regulator as a voltage divider, we're modeling a set of semiconductors that we haven't talked about yet, but it's a set of semiconductors as a mechanical switch that can connect a pole to 2 different throws. And so carrying this over to our linear regulator analogy, we have our unregulated voltage on the left side, and we are going to connect this pole to the different throws to achieve a regulated output voltage VDC on the right side. So let's now talk about the operation of this and what the waveforms look like. And I'm going to define time intervals where the pole is connected to the various throws. So let's say that in this first interval here, throw 2 is on. That means that the pole is connected to throw 2. The switch is in this position here. In the second interval, we'll say that throw 1 is on. So that means now that the switch is connected to the top throw. And in the next interval, we go back to having throw 2 on, and then throw 1 on, and so on and so forth. So this repeats. This is a repeating set of events. So on the top here, we'll sketch our voltage, and on the bottom, we'll sketch our current. First of all, we can draw a line that represents the voltage across our throws. So the voltage across our throws, that's the voltage T1 minus the voltage at T2, is always VT. That's the DC voltage because we've set the problem up that way. We put a DC voltage source there. Well, now on this graph, let's label our pole voltage. And so during the interval when throw 2 is on and the switch is connected like this, you can see that the pole voltage has to be 0 volts. The pole is directly connected down to the return. But during the interval where throw 1 is on and the switch is in the top position, the pole voltage has to equal the throw voltage. And then again, we hit to interval 2, where throw 2 is on and throw 1 is off. So our pole voltage goes back to 0. And this repeats. Now let's sketch our current. Clearly the pole current always has to be capital IP because there's a DC current source there. And we can sketch each of the individual throw currents separately. So throw current 1 that's the current over here, is 0 when throw 2 is active and throw 1 is inactive. But then clearly, as soon as the switch goes to the top position, throw current 1 has to equal the DC current source. Throw current 2 is going to be the opposite. When throw 2 is active, clearly the current path has to go up around like this to satisfy the DC current source. So throw 2 equals the DC current source, and then when throw 1 is active and throw 2 is inactive, the current through throw 2 goes to 0. So it looks like the opposite of the waveform for throw current 1. So the quantity of T1 on, that's the time that throw 1 is active and throw 2 is inactive, over the period, which is T1 on plus T2 on, can be expressed as a duty ratio. So Ts is our switching period, and this quantity is the duty ratio of T1, which is the time that throw 1 is on. And we'll call this quantity D1. And we can use this to evaluate the average values of the waveforms that we just graphed. So clearly, the voltage at our pole, which was this quantity, we can calculate the average of that in terms of D1 and the throw voltage. So this has an average value that looks something like this. And I'm putting the bar over the top of the quantity to indicate that this is an average expression. So for the T1 on portion of this waveform, Vp is equal to V throw, and for the T2 on portion of this waveform, Vp is equal to 0, which clearly results in this expression that the average value of Vp is equal to D1 times the throw voltage. And we can do a similar thing for the currents. So in green here, we had our throw 1 current, and in purple we had our throw 2 current. So similar to the voltage, the throw 1 current is at the output current when throw 1 is on, and it's 0 when throw 2 is on, which means that we'll have the same average value relationship to the pole current as our pole voltage did to the throw current. So, and our second throw current also has an average value, and the average value of IT2 is going to be the duty ratio of that waveform times the pole current. Okay, so what can we conclude about this operation? Well, we can say that this single pole double throw switch is behaving like a voltage divider, but only in the average sense. The instantaneous pole voltage is always either at 0 volts or at the throw voltage. But if we take the average of that pole voltage, we find that we can transform the value of it by selecting an appropriate duty ratio. So we can go between 0 volts, where D1 is 0, or the throw voltage, in which case D1 is 1. So this is similar to the linear regulator in that we're stepping the voltage down. The second thing that we can observe is that this is going to have high efficiency. Because our switch is either always on or always off, that means our resistance is either infinity or 0. And the final point, we can have bidirectional power flow. So I expect this observation is not intuitive for you based on the presentation so far, but it's true, and we will be developing it as we go. This means that we can have power flow that goes from the high voltage side to the low voltage side, or power flow that goes from the low voltage side to the high voltage side. In this video, I've introduced you to a new approach to voltage conversion. In this approach, we take a DC voltage source and we chop it up into a square wave voltage. We vary the pulse width of our square voltage waveform to achieve a desired average output voltage value. This is called pulse width modulation, and the energy conversion approach is referred to as switch mode electronics.